Hello, my name is Charlie Walker. I'm a high school senior, and I'm making a YouTube series going through all the units of calc to help students study for their classes and pass their exams. Today, I'm going to start with Unit 1, and the first topic of Unit 1, Unit 1.1, is can change occur at an instant? And what does this mean, right? So let's say, for example, we have a graph. This graph is a graph of f of x equals 2 square root x, or y equals 2 square root x, right? The slope on this graph, it starts off very steep and it kind of levels out. Change just means slope. So change at an instant means slope at one specific instant. So for example, if we take the point 1, 2, which is right here, point 1, 2, you want to find the slope at this one point, right? You would want to find the slope that touches the line at this point and continues with the slope that's going right here at this one specific point. It would look like this. So at the point 1, 2, this line right here that we made is called the tangent line. This represents the slope at that one point. In pre-calc, we learned how to find the average rate of change. This right here is called instantaneous rate of change. That's a very important term you need to know for calculus. I'll type it out so you can remember. You can take notes. Instantaneous rate of change. It's a very important term. In pre-calc, we learned how to find average rate of change. So if you want to find the slope of the average rate of change over any type of distance, we learned this in pre-calc, is f of x2 minus f of x1 over x2 minus x1. So, for example, if I took the point 4, 4 and wanted to find the average rate of change from 4, 4 to 1, 2, the slope of the line would look something like this. It's kind of similar to the slope of the red line because it's like next to it. It's further from our tangent line that we made, but it's a little bit similar, right? So if you plugged in the numbers, f of x2 at the point 4, 4 is just the y value. So you would have 4 minus f of x1, which is the y value at 1, which is 2, over 4 minus 1, because those are 2 points. If you plug this in, you get 2 over 3, or 0.66 repeating, right? So the slope of this line that we made is 0.66. If we wanted to get something more accurate, something closer to the instantaneous rate of change, the slope at that one point, we would have to get closer to 1. Like 4 to 1 is very far apart. We want to get closer to 1. So if we went, for example, 3 to 1, right, and we wanted to find the slope from x equals 3 to x equals 1, right, from 3 to 1, we would get this line right here, which is pretty similar to the red line, which is the line of the equation, and it's getting closer to the slope of our tangent line that we made. So once again, you have f of x2 minus f of x1 over x2 minus x1. If you plug this in, I'll save you a little bit of time and a little bit of calculator. You get 0.73, which is steeper than the line before, which makes sense because our tangent line is very steep. If we replace f of x2 with just another variable, we'll call it b, f of b, then we have f of b minus f of x over b minus x equals whatever the slope is, depending on how close you get. So if we pick numbers that are closer and closer and closer and closer to 1 to put as b, right? Because we started with 4, and then we did 3. If we put 2, which is closer, if we plugged it in, we would get 0.83, right? Which is, once again, steeper than the last two. So if we continue this, I put it into a table, so you don't have to. You would get a table that looks like this. From 4 to 1, you have a slope of 0.66. From 3 to 1, you have a slope of 0.73. From 2 to 1, you have a slope of 0.83. Once you start getting closer, you get 1.5. You have a slope of 0.89. Once you get really, really close, right? If you get 1.01, that would be the slope of like, here, I'll put it in red to make it, or I'll put it in blue to make it easier to see. If 1 is here, 1.01 would be like right here, right? So the tangent line would look almost exactly the same as the one we already have, right? You get a slope of 0.997. And if you go even closer to 1.001, the slope of that is 0.9997. So as you get closer and closer to 1, and you're comparing the average rate of change, the slope of the line that you're making is getting closer and closer to 1. Assuming the slope of the line is more of a concept in Unit 2, but the important part to know here is that as you're getting closer and closer and infinitely close to 1, you're getting a more and more accurate rate of change. And the reason why you can't just do 1, right, and use the point 1 and compare it to 1 is because you plug that into the equation, right? If you have f of 1 minus f of 1 over 1 minus 1, you would obviously get 0 over 0, which you just can't do that. Breaks all the rules of math. The world explodes, all of that. So as you get infinitely closer to 1, the slope you get is going to get more accurate. So in this equation, f of b minus f of x over b minus x, the closer that b gets to 1, the closer the slope gets. So if you wanted to find the actual slope of 1, you would need you just need to get infinitely close to 1. And in math and calculus, we call that a limit. And to wrap up this section, I have some practice problems here, some practice questions. So if you pause it now and you can look at this, you can write down your answers. You can skip ahead to when I answer it. So what would each of these mean in this situation? So in this case, m of t represents the number of miles a runner ran over a number of hours, right? So it's just how far someone ran in a certain amount of time. So what does m of 5 represent in this situation? In this situation, m of 5 means 5 would represent 5 hours, and m would represent miles. So how many miles did the runner run in 5 hours, right? That's all this means. M of 5 represents the distance ran in 5 hours. Okay, so what would m of 7 minus m of 0 over 7 minus 0 represent? This equation right here, this is the average rate of change formula. So it would represent the average speed of the runner from hour 0 to hour 7. And this one down here, lastly, what would this represent? It's a number very, very close to 6, approaching 6. So this would give an estimate, because it's not 100% accurate. You can find out how to do that in later units, of the runner speed 6 hours in. And that's it for this topic. Next up, we have defining limits and using limit notation. So what is a limit and what is limit notation? Limit notation is this right here. Limit f of x when x is approaching a equals L. This is how you read this. The arrow means approaching, f of x is your function, and L is going to be a value. All this means is that, let's say you have a graph right here. Let's say you have a graph with a straight x and y axis, first of all, and you have a line that looks like this, for example, right? And this is 1, this is 2, this is 3. When x is approaching a is just a value that it's going to give you. F of x is your function, and L is a number, right? So in this case, limit when x is approaching 1 of f of x equals, that just means that on the graph, when x is 1, because x is approaching 1 over here, what is the line like approaching from both the left side and the right side? So it doesn't matter where you look at this from. If you look at 1, you're going to end up right here, and let's say this is 1, right? So limit x approaching 1, f of x in this case will be 1. If this is 2 and this is 3, and we look at limit x approaching 2, f of x for this function, if you look up from 2, the line is approaching 3. So it would equal 3. I mean, that's just it. You just look at like where the line is at that x value. What's different though is that if you have a function, except there's a hole right here, and it keeps going. Let's say this is 1 now. Let's say it's not the same function. This will be 1, this will be 2. If you look at the limit of 1, limit x approaches 1 of f of x, it doesn't matter that there's not a real point here, because since it's an open circle, it means that from the left side, it's going to get infinitely close to 1. It's going to go to like 0.999999. And on the right side, it's going to be 1.0001. It's going to get really, really close to 1 on both sides. It's just never going to touch it. But if you're looking at the limit, you're not looking at the actual y value. You're saying that it's approaching it from the left. It's approaching it from the right. So the limit of 1, in this case, of when x approaching 1 is still 1, right? Even though f of 1, in this case, is undefined or does not exist. So it doesn't matter what the actual point is, as long as the limit is approaching it. In this same graph, if we look at limit f of x when x is approaching 2, there's a closed circle here, and you look at it from the left, it looks like it's going to 2. If you look at it from the right, it looks like it's going to 2. So it would be 2. And in this case, f of 2, look at the point on the graph, it's still 2. So either way, it's 2. So the point is, if there's an open circle, the y value of that point, or f of that point, does not exist. But for limits, it doesn't matter if it's an open circle or not. Now, as a bigger example, I'm going to pull up a big, super pretty graph. Let's look right here. Wow. So on this graph, if we were to look at limit f of x when x is approaching -5. There's an open circle here, and there's a dot here, right? Which one would we pick? If it's a limit, you're looking at where the line is approaching. You don't care about where the points are, really. So the line here from the left is looking like it's approaching -4 here, I believe. The scaling on this graph is wrong. Let's just say this is -2, even though up here it doesn't really agree. Let's say this is -2, right? Since the line is approaching this point from the left and from the right, the limit when x is approaching -5 would be -2. If we look at f of -5, right, then you want to look at this point here and you want to see, oh, it's at 3, so f of -5 is 3. I'm gonna let y'all do the rest of these. I'm gonna just write them. So if you have limit when x is approaching -4, f of -4, f of 0, limit f of x when x is approaching 0, f of 4, and limit x approaching 4, f of x. This last two are going to be a little bit tricky. Pause the video now if you want. Solve them. I think this concept is pretty simple. Is looking at the graph. One of the simpler concepts. But let's go through it. So limit of -4, if you look at the graph, from the left side, it looks like it's approaching 3. From the right side, it looks like it's approaching 3. So the limit f of -4 is going to be 3. If you look at f of -4 itself, there's an open circle here. So it's just not defined. It does not exist is what D&E stands for. F of 0, if you look at the graph, is at 0. Limit x approaching 0, if you look at it from the left and from the right, is still 0. F of 4, there's a closed circle here, so it's going to be 3. And limit x approaching 4 of f of x. This one is a little bit tricky, right? Because if you look at it from the left, and the line's coming up here, it looks like it would be 3. And if you're looking at it from the right, the line's coming up here, it's looking like it would be 5. So they don't agree with each other. From on one side, you have 3, and on one side, you have 5. And in that situation, it just cancels out, and it does not exist. That's literally it for 1.2. It's pretty simple, pretty fast. And we moving on.